I mean, for the next workshops until the end of the term, you won't have any coding. So if you want to use your laptop to write stuff, take notes, yes, it's up to you, but you don't have to have your laptops for the workshop until the end of the term. Essentially, we have week 7, 8, and 9 workshops. We don't have any workshops on week 10 because we started from week 1. There is no workshop in the last week. The last week we'll have a revision of the term, so we won't have any workshop. But as I said, it's up to you. If you want to bring your laptops, yes, of course, you're more than welcome. Otherwise, you don't have to. The slide that I have on the screen, this is, as I said, was asked, we as the module leaders, we were all asked by the quality team to share with you. It is recorded, so, and immediately you have the access to the recording. If you just scan the QR code, you'll have all the events which are organized by the quality team. Now, our topic today, if you remember last week, I told you this was the last week that we worked on integer and mixed integer linear programming, essentially modeling linear and mixed integer linear programs. So today we will cover an approach to solve mixed integer or integer linear programs that we call them combinatorial optimization problems. I'll explain you in a minute what does this mean. And on week 8 and 9, next week and the week after, we will focus on nonlinear programming. As I said, on week 10, we'll have a revision. Okay. And again, I mentioned in the workshops and in the lecture last week that you're expected to practice for modeling. I'm pretty sure that for the group assignment, you have a good practice on linear programming. Now, you know what are the differences of integer and mixed integer IP, MILP, and linear programming models. So it is your turn now to practice, and you can find lots of problems on the textbook. You can find too many sources and examples online, and you're always more than welcome to contact me if you wanted to check the solution that you have for a specific problem. Okay. Now, as I said, integer, there are different methods that we can use to solve linear programming. And I showed you one which was graphical solution method, which was a very limited one, essentially because you can use this only if you have two decision variables, and in real life, often you have thousands or millions of them. So it's not something that you can use. And I showed you when we started to use Piamo that we can see what are the approaches or which algorithm Piamo is using to solve linear programming. One of them was simplex method, revised simplex method is another one, and there are other approaches that can the solver that we have GLPK or IPOpt or GROBY or Cplex, they apply to solve linear programming models. This approach doesn't work simplex method or graphical solution method. If you remember, I told you simplex is somehow similar to graphical solution method because it goes from one corner point to another one to find the optimal solution. This approach is not applicable to integer programming models because this feasible region is completely different. The feasible region that we have in a linear programming is all different points that we have within the feasible region. When you go from one point to another point, you never leave the feasible region. This is unlike integer or mixed integer linear programming models where we have integer solutions. Therefore, when you go from one point to another point, essentially you go from 1 to 2. When you want to go from 1 to 2 on your way, you pass the points which are not integer points, which are not a part of the feasible region. So it is essentially different from linear programming. There are different methods that we can use to solve these models. I will cover dynamic programming because this is one of the methods that we will cover or use for pricing analytics, which is one of the elective modules that we can take for next term. You already, I guess, chosen the module that you want to pick for next term. That's why we cover this one. There are other methods like branch and bound as well, but we won't cover it. It's simpler than dynamic programming, so I thought that dynamic programming is better to be covered here. Okay. Now, dynamic programming is a technique used to solve many combinatorial optimization problems, such as scheduling, inventory management, and resource allocation. Some of them are the examples that you will solve in workshop, like scheduling. Some of them are the ones that resource allocation, sorry. Some of them are the ones that you will have the answer for them, so it's a practice for you to do. What do we mean by combinatorial optimization problem? If you remember from knapsack problem, which was the problem of selecting items based on their values and sizes, because we have a limited size of a knapsack. And I told you it looks very simple because we have different options, items that we want to pick. And for each of them, we're going to decide whether or not we're going to pick them, 0 or 1. And there is only one single constraint that we have. The summation of the sizes should be less than or equal to the capacity of the knapsack. It looks very simple, but it's not, because we have many different combinations of the items that we can pick. You may, based on the size, you may only go with a single item in the knapsack, 2 items in the knapsack. If you have 2, and there are like 10 different options that you have, the pair of 2 out of like 10 that you have, it's a lot. 3, 4, 5, 6, 7, 8, 9, and 10 might be also the case. This is just for 10. If you have more, the number of combinations that you will have, it will be the 0 ones that you have essentially for n items becomes 2 to the power n, which increases drastically when you increase n. So when n is um, multiplied by 2, the number of options that you have is a lot. That's why we call them combinatorial optimization problem. It's not easy to solve them. If you use any essentially any regular solvers like Groby or Cplex or IPO, it may take ages to solve the problem. That's why we use dynamic program, because it is faster. Why it is faster? Because it works by breaking up a large complex problem into a sequence of smaller interrelated problems. There can be a relationship across sub-problems. We call them sub-problems. So you have this complex problem, which is a massive one. You just break it down to sub-problems, 1, 2, 3, until n, and then we solve these sub-problems. Why we do this? Because solving these sub-problems are easier than solving the complex problem. The sub-problems, the smaller problems that we created, are interrelated to each other. There is a relationship in between them. We'll see how it works. For dynamic programming, we start by structuring the problem as a sequential decision process. It becomes a multi-stage decision-making procedure. We start with the smallest, simplest sub-problems, and then we solve the others until we solve all different sub-problems that we have. So essentially, we have this complex problem that we have. We break it down to sub-problems. Among these sub-problems, we choose the one which is the simplest or smallest sub-problem that we have, that easily we can solve it. We solve this one, we move to the second one, the third one, the fourth one, the fifth one, or just order them based on their the level of how hard they are to be solved. The first one, sub-problem one, is the easiest one to solve. The second one is harder than the first one. The third one is harder than the second one, etc., etc. We solve all of them. Once we have the solution to the sub-problems, we combine the solution that we obtained from the sub-problems to find the solution to the larger or the original complex problem that we have. So combine sub-problems to obtain solutions to larger sub-problems until we get the solution to the original or the largest sub-problem we have. So here what we can see is that there is a relationship in between these sub-problems. So your solution to sub-problem 1 somehow impacts the solution in sub-problem 2. Sub-problem 2 impacts sub-problem 3, etc., etc. Okay. Now let's start with an example. Let's assume that we have 4,000 to invest, and there are like 3 investment options available. The amount invested in each option must be exact multiple of 1,000. So we can go with 0, 1, 2, 3, and 4,000 as the investment. You can go with 1.5, for instance, or you can go with 2.1. Yeah, it's the exact multiples of 1,000 here. For instance, if we and here we can see in this table what we have. Depending on the investment amount, we see for each of the investments, A, B, and C, how much we will have the return. For example, if we invest 2,000 in option B, in option B here, 2000, the return amount is 3 multiplied by 2000 plus 1500, which gives us 7500 in return. Okay, so you can see here that we have two rows. The first row gives us the return when we have some amount invested, if the amount of investment is positive, and on the other hand, we can see that it is zero if there is the return is equal to zero if there is no investment, obviously. Okay. How should we invest 4,000 to maximize the return? This is the problem that we have. We want to solve it. It's not a hard. It is not hard to solve this problem. Okay? This isn't a very easy problem to be solved, but just to see how dynamic programming works and how we can generalize it to a larger problem, we have this example because we want to write it in a piece of paper to see how it works. Remember that we did the same with graphical solution method. I did it because I wanted to show you how optimization for linear programming works, how simplex method works. That's why I showed you graphical solution. That's the same. It's a very small problem. Easily we can solve this problem, but it is nice to see how the steps of dynamic programming works. Okay. Now, here what we have, pen and navy. So, oh, didn't open it up. Sorry, I have my tablet, which is not. Okay, now it is. So let's PI be a non-negative amount, which is multiple of 1,000 of investment in option I. The problem that we have here, the model that we have here, is the return that we will get from each of the return that we will get from each of the options. Option 1 essentially is RAP, and PA or PI is either 0, 1, 2, 3, 4, because we know that it is multiple of 1,000. So that's why we just wrote it as 1,000 multiplied by PI, because PI itself is 0, 1, 2, 3, 4. And this is the function that we get as the return for investment A, investment B, investment C. We know that the total amount of investment PA plus PV plus PC should be should be equal to 4. This is the total amount of money that we have. And we know that P1, P2, and PC should be greater than or equal to 0, and they are integer. This is the problem that we have. What do you think? Is this an integer problem? Is it integer? What do you think? Just write it on the chat box. Is it integer? Yes, it is integer. Yes, it is integer because the string variables can only be multiples of 1,000. It is integer programming. Okay. How about linearity? Is it linear? Is it linear? Yes, no. Why no? If you say no, why it's not a no? At the same time, I'm trying to get yes and no. What does that mean? You can see that for each of the the tablet doesn't work. I don't know. It's working the other day. You can see from this one here. So they seem to be linear, right? This is 2p plus 2p plus 2,000. This is like 3p plus 1,500, etc. The function that we have here, you can see that for each of, so the objective function is a mixture of like 3 of them, any number of the investment that we have. So sorry that it's not the best because my tablet doesn't work. So you can see for each of them, the slope is different. Okay, and the slope is different for each of them. Yes, they are linear, but we call them piecewise linear functions. For instance, the first one is like this. Second one is like this. It is linear. Accept it from me that this is linear. But each of them, they have a different slope. We call them piecewise linear functions. We'll see in nonlinear programming, a linear function, having an objective function as a linear function. It is important because we want them to be differentiable in all points. And when you have piecewise linear function like this one, where the slope of different parts are different, for these points that we have here, for instance, this one, you can see because the slope before the point and after point are different, this function is not differentiable. That's why this function is not linear, it is piecewise linear. So we can use the regular integer programming methods that we had to solve the problem. That's why we use dynamic programming. On the top of that, as I said, when you have too many numbers of like alternatives for the investment, the number of alternatives becomes so high. That's why solving the problem becomes really hard. Now, let PI be amount of investment on option I in 1,000. Now, if you have this problem, which is R1P1 plus R2P2 plus, we don't have 3, we have n investment options. And then the summation of P1 plus P2 until Pn should be equal to W, which is the total amount of money that we have. Which problem would you consider as trivial one or the simplest one to solve the problem? How would you break this problem down to smaller problems? And then which problem would become the simplest one to solve? What do you think about this? P1 plus P2 plus, this is the constant, right? So what we have here in the objective function, we have the return from different investment. This is the total amount of investment that we have that we can just distribute among these alternatives that we have. How would you break down the problem? Would you be able to solve each investment separately, let's say? By each investment. Yes, that's fantastic. By each investment, you want to decide if you have this much money, how would you, if you have this much money available, how much would you invest on the first investment? If you have this much remain, how much you're going to invest on the second one? If you have this much remain, how much you're going to invest on the third one, etc., etc. Given this, what do you think? Which one becomes the easiest one to solve? And obviously, there is a timeline here. You start with the first one, let's say. The first one, for example, when you're investing on the first one, you have to keep an eye on the other investments as well, right? When you're going to say that I have W4000 and you're going to start with option A, you have to keep an eye on option B and C, because if you put all the money that you have on option A, you won't use the fact if they are more profitable, how much return that you can get from option B and C. When you decided on A, you have some money which remains for B and C. Now you're on B. You have to keep an eye on C as well. How much money you're going to invest on B, how much you're going to leave for option C. And when you're on C, you know, whatever you decide on the first two ones, so how much money you have to decide to see how much money will give you the maximum return from this last option that you have. So which one becomes the easiest one to solve? Option A, that you have to keep an eye on B and C. Option B, that you have to keep an eye on the C, or C, which is the last one. You already decided on everything up to that point. Now it's just the time for you to see how much you're going to invest on C, or the last one, essentially. Okay? Because in the first one, you have to keep an eye on the next ones, the second one, next ones, in the third one, next ones. But when you're in the last one, you already know whatever you decided on option A, B, C, D. Now you have some money which remains, and you're going to invest the amount which maximizes the return of the last one. So as it was mentioned in the chat box, this is the last one, the maximum of RNPN, where Pn is less than or equal to K. K is the remaining money after investing on all other investments. Now, this is the timeline that we have. Okay, we said that we want to break the problem down to different investments, investment A, B, and C. We are here now. This is the beginning. We have all the money that we have, 4,000. We have to decide how much to invest in option A by considering B and C, which means that you have to keep an eye on B and C. If you put all your money that you have invested on A, you won't have any return from B and C, which might be more profitable than A. Then you decide to put PA here, and then you will have 4,000 minus PA, which remains for B and C. You're here now. The remaining money that you have, which is 4,000 minus PA, will be remain for B and C. Now here you have to decide on option B by considering option C, which is the next one. When you're here, you already know that you put PA and PB for options A and B. The remaining money that you have is 4,000 minus PA and PB. Now that's super easy to decide how much you're going to invest on this one. Now let me get rid of this that I wrote. We start by identifying the subproblems. Subproblems are also called stages. In dynamic programming, we have some stuff that we need to define. The first one is the stage or the subproblems. The subproblem is the one that we can break down the problem to them so that the problem can be solved easier. We call them stages. The stages should be chosen such that when only one stage remains, the problem becomes super easy to solve. So subproblem or stages that we have for this one. The subproblems here or the stages of this problem are different investments, because I know when we come to the last investment, it becomes super easy to solve the problem. Does the order matter if you start from A to B and C? No, it doesn't. You can start from C, B to, the first one becomes like B, for instance, then C here, and then A here. It doesn't really matter. What matters is the last one, whatever it is easy to solve. Structure the problem as a sequential decision process. Why it is sequential? Because when you are here, when you decide on A, let me again erase this slide. When you are here, you decide on A by thinking of B and C. When you are here, you decide on B by thinking of C. When you're on C, this is the last one. C, when you want to make a decision on C, you don't need to consider anything else because it's the last one, but your decisions on A and B impact the remaining money that you have for C. But that's why it is sequential. Now, what we do here is we always start with the last subproblem, the smallest one that we have. Stage 3, we call it. We start from here, we go back to this one, and then we go back to this one. This is the process of dynamic programming. In reality, you start from A, you go to B, you go to C. We know this. In dynamic programming, we go backward. Why we do that? Because we want to see the different decisions that we can make for A in the first stage or for B in the second stage, how they are going to impact our decision in the last one. For example, if you decided to invest 2,000 in A and 2,000 in B, there is no money that you can invest on C. Okay? If you go with 1,000 in A and 2,000 in B, now you have 1,000 that you can invest on C. So this is, we are going to write it down as different combinations that if I do this in A and this in B, what will happen to C? And we do this backward, okay? We want to see if this much is remain, how we are going to make a decision for this specific one. For a given stage, subproblem, what is the optimal investment decision that we want to make? Our decision depends on the available money that we have. So as I said, if you use all the money that you have to invest on A and B, there is no money that you have to invest on C. If you decided to just leave 2,000 for C, then it changes your decision or the return that you will get from this sub-problem. What do you mean by order doesn't matter? Is it for all problems or some problems order centrally matters in real life? In reality, there might be an order that you have. For dynamic programming, what I said is we just broke down the problem to subproblems, A, B, and C, we call them. and we are starting from C. You could break it down to B, C, and A, and then the last subproblem becomes A. It doesn't matter if A is the last one, B is the last one, or C is the last one. That's what I said. In reality, if there is an order that you have, then you have to follow it, obviously. But for this specific problem, there is and no difference if the last one or the first one are different. Subproblem 3. If you have 4,000 available, what is the optimal investment amount in option C? For this specific problem, as I said, it's super easy. When you have 4,000 available for this option, you're going to put them all in this option because the return is something which is positive with positive coefficient. It's like 4p plus whatsoever it was. The investment amount that can be applied here are multiples of 1,000. So if we have 4,000 available, then we can invest 0, 1, 2, 3, and 4. Since we want to maximize the return, optimal investment is 4,000 with RC 4,000. If the investment amount is 4,000, it becomes 4p plus 500, which gives us 16,500. It is super simple, right? That's why we're going to do this. We start from the last one because this is the easiest one that we have. However, I don't know if I have 4,000 available. We assume that if we have 4,000, how much we're going to invest, which is 4,000. This is the remaining money at stage 3. 4,000 is the remaining money at stage 3. It can be 4,000, it can be 3,000, it can be 2,000, 1,000, or 0, depending on the amount that we invested on options investments A and B. For subproblem 3, or stage 3, how much to invest in option C by considering the available money we have, which we call it as a state. Stage is the subproblem. State is essentially the amount of money which remains. What is the state of the problem now? You have 4,000 remaining, 2,000, 3, 1, or 0. Our aim is to maximize the return. Now, in dynamic programming, we have some equations that we have to write. Okay, for our investment C, we know that if PC is greater than 0, then we have this return. If it is equal to 0, obviously, if you don't put anything, you won't get anything in return. And F3, X3 is the maximum return that can be obtained at stage 3, given that we have the state of X3. Okay. Now here, X3 is the available money we have. This is the state, and it is a parameter because I know X3 is equal to 4,000 minus PA minus PB. This is the remaining money. This is a parameter. So I'm going to solve them in the order from A to B to C. Now I'm going backward, and I want to consider different situations that can happen. PC is the amount of money invested in option C. So in dynamic programming, we have a stage, which stages are the subproblems. State or the parameter. State is the parameter for this specific problem, which is the amount of money which remains for this specific stage. And there is a decision to be made. This decision is to decide how much money we are going to invest on this specific investment at this stage, given the state being X3. We want to maximize the return, which is RCPC, given that PC is less than or equal to the available amount of money that we have. So we want to maximize this subject to PC less than or equal to X3. This is exactly the optimization models that we wrote. Maximize for PC plus 500, subject to PC being less than or equal to X3, and PC should be greater than or equal to 0 and integer. Okay. So here, remember that X, you always use decision variables as X, but here X is not a decision variable, it is a parameter. Okay. Now, can you tell me if Fx3, this one, F3, X3, is an equation at the end of the day when we solve the problem? What is F here? Is it a function? Is it a number? What is F3, X3? It's a number, exactly. Because you will have X 3, which is an input, it is a parameter. For instance, if you have a function which is fx equal to x, 2x plus 3, then x is equal to 4, for instance. F becomes 2 multiplied by 4 plus 3. So that's the case here. When you solve the problem, you will have a maximum return, and this f3, x3, is a number that you will get at the end of the day. Now, in stage 3, we will form this table. This table that we have here, this is what we have. In the rows, we want to have different states. We are in stage 3. The parameter here, or the state, is x3. And this x3 can be different values. If you decided to invest all the money that you have on investment A and B, you will have 0 remained. If you decided to go with 2 and 1, then you will have 1. If you go with 1, 1, you will have 2. If you go with 1 and 0, you will have 3. If you decided to go with 0, 0, you will have 4. So I have all different states that I may have in stage 3, which can be 0, 1, 2, 3, and 4. And then, according to these states, I have different decisions available that I can make. If I have 0 available, I have no decision to make. PC will be equal to 0. If I have 1 remain, I can decide if I want to invest this 1 in investment C, or I don't want to invest anything on this investment. Again, this problem is super easy. That's why, yes, if you have 1, you want to obviously invest all the money that you have on this one. If you have 2, you want to invest 2, because this gives you the maximum that you want, you want to get from the return. But there are examples that we will see that it's not always the case. Now, here, as I said, these are the states of the problem, the different states that we may get at this stage. These are the decisions that we are going to make. Now, let's assume that we have 2 available. Okay? We decided to go with 1 in option A and 1 in option 2, which leaves us 2 for option C. If you have 2, you can decide 0, 1, or 2 on this in this investment. If you go with 1, how much return you will get? If you go with 1, it is 4 multiplied by 1,000 plus 500, which gives me 4.5 thousand. If you decided to go with 0, you will get 0, obviously. If you go with 2, that's the formulation that we have. If you go with 2, it's 4 multiplied by 2,000 plus 500, which gives me 8.5. Can I invest 3? No, because the state that I have on this stage is 2. I can't go with more than 2. So what we do here is we fill this table, and for each of the row, which gives me different decisions for a given state, I will find the maximum return that I can get, and I will find which decision gives me the maximum one. So for this one, the maximum comes from the decision which is PC being equal to 2, because this gives me 8.5, and this is the maximum in this row. Now we fill this one by one. If we have 0, obviously 0 is what we can get. The maximum is 0, and it comes from 0. If you have 1, there are 2 alternatives that we have. We can go with 0 or 1. If we go with 0, we get 0. If we go with 1, we'll get 4 multiplied by 1 plus 500, which is 4.5. And the maximum is 4.5, which comes from an optimal decision of 1. If you have 2, we can go with 0, 1, and 2. There are different values that we can get. If you go with 3, if you have 3, essentially we have different decisions that we can make here: 0, 1, 2, and 3. If you have 4, we have all different alternatives, and then we can see among them the one which maximizes the return is this one, which is 4, as essentially investing all money that we have on this investment. Okay, so this is essentially, I'm at stage 3. At this stage, I know I made decisions on A and B. Based on the remaining money that I have from these 2 stages, I want to make a decision. Now I'm just here, I'm just considering different amounts that can remain for this specific stage, which are 0, 1, 2, 3, and 4. Could you please repeat what is the state, the possible value range for decision variable at certain stage? No, state is a parameter which is remaining money at this stage. Okay, we have 4,000 from the beginning. We have option A, B before C. We are at stage 3, which is investment 3. Now I have to decide if you're going to how much money you may have at this stage, which becomes a state. State might be zero, which means that you decided to invest all the money that you have on investment A and B. You may have one remain here, which is like you decided to go with 3 investment A and 0 investment 2, and so on and so forth. So there are different there are different combinations of decisions that you can make and for a stages 1 and 2, which impact your remaining money for a stage 3, which is your state. Okay. Now we keep this information, which is the maximum or optimal decision for this stage based on the different state or remaining money that we have from stages 1 and 2. Okay, what we want to do here is essentially we want to see if you decided to leave no money for stage 3, how much money you can earn at the last one, which is 0. If you decided to leave 1, how much money you can get in stage 3. And based on this, you make a decision for a stage 1 and 2. Now, we did stage 3, investment 3, but looking into different possible values, states, which are the remaining money after investing on investment A and B. Now, we know this one. We said that we keep this information that I showed you in the previous one, this one. We keep this information. We bring it to stage 2. In stage 2, remember that we want to decide on option B by considering option C. By considering means that if you decided to invest all the money that you have on option B, then you will have no money to invest on the last one. So the return that you will get from the last stage or investment C becomes equal to 0. Okay? When you are at this stage, what do you know for sure? What do you know when you're in stage 2? Can you write in the chat box? What do you know when you're on stage 2, when you want to decide on B by considering C? What do you know? What do we know? Exactly, we know how much money we have invested on A, so the remaining money is now. Again, we are going to do the same. We are going to consider different possibilities of remaining money for option B, which can be 0, 1, 2, 3, 4. And then we decide on how much we're going to invest on B. For instance, we'll see now. I'll show you rather than saying you. So remaining money at stage 2 is less than or equal to 4,000. You may go with no investment in option A, which remains you 4,000 for option B and C. So the money that we will have here can be 0, 1, 2, 3, and 4,000. In stage 2 or subproblem 2, which is investment B, let's assume that we have 2,000 available after investing in option A, which means that we already invested 2,000 in option A. How much money we invest in option B by considering option C? We have 2,000. The possible decisions that we can make is 0, 1, and 2,000. These ones are the possible decisions that we can make. The state here is 2,000, the remaining money for this stage. If we decide to invest 2,000 to option B, the remaining fund for option C becomes equal to 0. And when we have 0, because I brought this table, when we have 0 remained for this option, I know that I will get only 0 from this investment. This is what we mean by considering the next one. So PB plus PC becomes less than or equal to the state that we have. So it's not only deciding on how much money we are going to invest on B, but we want to consider how much we are going to leave for C. The optimal investment amount in option B depends on our decision for option C. Essentially, how much money we are going to leave for option C. We do the same given the optimal solution for stage 3. How much to invest in option B, because I have this table that I brought from the previous stage. We define F2x2, which is the maximum return that can be obtained at stage 2, given that we have x2 amount of money remaining after investing on investment A. X2 is the available money for option B and C. This is the state. PB is amount of money invested in option B. This is the decision that we have to make. We write this one, which is maximum of RBPB plus F3 X3. X3. So we know that we came to this stage with X2 remaining money after investment made in option A. So it's 4,000 minus PA itself. This is X2. And if I decide to invest PB amount of money for option B, I will leave X2 remaining money at this stage minus PB for the next stage. If I have 3,000 remain for option C, I can check the table that I have and I can find what is F3, X3 in terms of number, because F3, X3 is a number for different values of X3. So we want to maximize this. This part depends on the value of PB, as you can see. X2 is now, I know how much money I have. PB is what I'm going to decide. The remaining money for option C, I have this one. I check the table and I can find how much I can get as the return. Now, we form this table again for stage 2. Here again, we can get 0, 1, 2, and 3, and 4 as the possible remaining amount of money after stage 1 or option A, investment A, because you may decide to invest nothing in the first investment, so you will have 4 remain. If you decide to put all your money in investment A, then you have no money remain for B and C. Now here, let's say you have 1 remained from option C, so option A, sorry. You decided to invest 3,000 in investment A. Now you have 1 remained here. This is your state. If you have one here, you can decide 0, no investment option B, or all money being invested on investment B. If you invest all your money on B, this means that you leave no money for alternative C, investment C. So if you go with this one, from investment B, you will get 3PB plus 1,500, which leaves you 0 for investment C. If you have 0 remained for option C, the maximum that you will get is 0. If you decide to not invest this 1,000 on option B, you will get 0 from option B, but you will leave 1 for option C, which gives you 4.5. So you can see here for each of the cells that I have 2 numbers. The first one is for option B. The second one is the maximum return that you can get from investment C by considering the remaining money after investment of option or investment B. For example, here 3. If you have 3 remained, you decided to go with 1,000 on option A, you have 3 for B and C. At this point, you can go with 0, 1, 2, and 3. If you decided to go with 2 in option B, then you will get 3 PB, 3 multiplied by 2 plus 1,500, which gives you 7.5. And if you invest 2 on investment B, you will have 1 remain for investment 3, which gives you 4.5. So now among them, again, you will decide which one is the maximum one that we have and what investment gives me this maximum. Again, we do the same. We keep this information that we have here for different states, how much I'm going to get as the maximum based on what decision that I made. I carry this one to the next stage. Now, I decided I know what are the possible, based on the possible states that I may have on investment C, the possible states that I can have for option B and C. I have different combinations of the decisions that I can make and the maximum return that I have. Now I will go to option A. When I want to make a decision at this stage, stage 1, I have to keep an eye on B and C, because now I know if I decide to go with 4,000 on this one, I'm going to leave 0 to this one and 0 to this one. And if that's the case, I know how much maximum return that I can get from this one. If I'm going to leave all 4,000 here, let's say 4K, I leave it for these 2. I know now with different decisions that I can make here. I can go with 0 here, 4 here. I can go with 1 here, 3 here. I can go with 2, 2, 3, 1, and 4 and 0. And I know among them what is the maximum that I can get. So you can see that based on the number of options that you have, based on the different state space that we have, we may have too many decisions options to make. Here it's so simple because we have just 0, 1, 2, 3, 4 as the possible investment amounts that we can make. If it was more, like if you could go with 100, 100, you would have too many different states here. It's just 5 of them that I have here because we just said that we can invest as multiples of 1000. Now, when we are in stage 1, what do I know? Is there anything that I know when I'm in stage 1? When I want to start by investing in investment A, do I know anything beforehand? You said when you're in stage 2, I know the amount of money that we invested on A. But when you're in A, is there anything that we know beforehand? No. And what are the possible states? For B and C, what we had was 0, 1, 2, 3, 4. For C also, stage 3 also, it was 0, 1, 2, 3, 4. How about investment A? What are the possible states that we have? Is it again 0, 1, 2, 3, 4? Think about it for a minute. Think about it for a minute. What are the possible states in the first stage? If there is no decision to be made beforehand, how much money I would have in for the first investment? 4,000, exactly. There is no decision. So the possible state that we have for the first stage is the whole capacity that we have, 4,000. That I'm going to invest on A, B, and C. I'm going to decide for A by considering B and C. I'm going to consider B and C because I have these tables that I brought from the previous stages. Now in stage 1 or subproblem 1, given the optimal solution in stage 2, how much we are going to invest on option A. We define FAXA1, F1 X1, which is the maximum return that we can obtain at stage 1, given that we have X1 amount of money. X1 is the parameter, and it is the available money for options A, B, and C. PA is the decision that we are going to make. The formulation is like this. It's maximum of RAPA plus F2X2. Remember that F2X2 was the maximum that we can get from option B. How about C? Why C is not here? Because I'm saying that I'll make a decision on A by considering B and C, but C is not here. It's just B. F2x2. If I go back on the slides, you can see that F2x2 is the total, is the maximum return that we can get on a stage 2 based on the available money of x2. Because here what we have in the second stage, you can see that I considered both of them. The second term that I have here is considering the money that we can earn from investment C. So F2 already includes FC as it is written. Very good. That's very good. Just continue. So it's a single row that we have because the number of states that we have here is just 4. There is no decision before us. And there are different, essentially we have different decisions to make. If you have 4, we can go with 0, 1, 2, 3, and 4. If you go with 0, here, if you go with 0, you're going to leave this 4 for the next stages. And if you have 4 available for B and C, you will get 17. If you decided to go with 1, you will get 4 from this one. And you're going to leave 3 for the next ones, which gives you 13. So you just write them for all different options that you have. You can see that 17 is the maximum that we can get. And this comes from 0 and 1. If you go with 0, here and 1 here, you will get the same solution because both of them will give you a maximum return of 17. This is the one that I wrote in stage 3. This is the one that we wrote in stage 2, and this is the one that we wrote for stage 1. I wrote this one because this was the last one, the easiest one. Or use this information to form this one, or use this information to form this one. Now, what is the optimal solution? What do you think? What is the optimal solution? How much you have to invest in A, B, and C? And what is the maximum return that you can get from these decisions? Two optimal solutions, that's good. What is the optimal objective function value, the maximum return? Fantastic, great. So we have multiple optimal solution here, two of them, essentially 0 and 1. Because if you go with 0 here, you're going to, let's say that we go with 1,000. Invest 1,000 in option A, leaves 3,000 available for B and C. If you have 3 available for B and C, the optimal decision for B is to invest 1 here, which leaves 2 to the last one. This is what we have. If you have 2 for the last one, you're going to invest all of them in option C. Your optimal objective function value is not summation of them, because this 17, as you said, includes F1, X1, includes 2 and 3 as well. If you go with 0 here, you're going to leave 4 for the next one. If you have 4 for B, the optimal action is to invest 1 here, which leaves 3 to the next one and gives you 3 as the optimal solution. Okay, so both of them will give you the same optimal objective function value. You can see here, I told you, it's not possible for a linear programming model to have exactly 2 solutions, but for IDP and mixed integer linear programs, it is possible. It doesn't need to be 0, 1, and too many, which was the case for linear programming. For integer programming, you may have 2, 3, 4 optimal solutions. So the features of dynamic programming problems, the problem can be divided into stages, and we make a decision at each stage. Each stage has a number of states associated with it. The stage includes the information that is needed to make an optimal decision. The states correspond to the various possible conditions in which system might be. Here it was the investment on the previous investment that we had. The decision at each stage transforms the current state into a state in the next stage. Example that we had here, for instance, we have 4,000 and we decide to invest 1,000 to option A. Our decision determines the state at the next stage. So at stage I, we have the available resources as xi. Our decision is pi. So we know that the next state in the next stage is previous state minus the decision that we made here. So that's why they are connected to each other. Principle of optimality, given the current state, optimal decision for the remaining stages dependent of the decisions adopted in the previous ones. Remaining money essentially that we have at each of the stages. Fantastic. Dynamic programming is shortest path problem is one of the famous problems that can be solved with dynamic programming. So just put it here because shortest path is very famous and often used by the companies and industry. Great stuff. I'm going to stop here. If you want to leave, you can leave. But if you want to stay and ask questions, you're more than welcome to ask questions. If you're leaving, I won't see some of you on Wednesday. I will view the rest of you, hopefully, on Friday. Otherwise, I will see you all next Monday for the online lecture. Take care. Feel free to ask your questions on the chat box. No worries, guys. If you have any questions, just fire it away. It might seem a bit, we'll solve a few questions, so you will see that it's not that tough. but it might seem a bit like weird to understand the order, solving backward, those stuff becomes easier when we start solving a few questions in the workshop. Could you repeat why in stage we only use 4? In stage 1, you mean, I guess. Yes. So remember that if I go back to the stages here, this one, let me just get rid of the ink. So what we have here is you have to think of this in this way. We are going backward, okay? When you are here, in reality, this one was decided, and then we came here. In dynamic programming, I'm going backward to just consider different decisions that I can make based on the different possible states at each stage. Okay, when you are here at this point, you know the decision here has been made. So you know how much money you decided to invest on option A. So you know how much money is remained out of 4,000 that initially you had for this stage. When you are here, there is no decision to be made before you. That's why the 4,000 that you have is here, and you have to decide how much you're going to invest on A and how much you're going to leave for B and C. That's why we only have one state here. One state here, yes, of course, 4,000, which is different from this stage. At this stage, stage 2, you may have different values because there was a decision which was made at stage 1. 4,000 you decided to put some money PA in stage 1. Now the remaining money is the state of stage 2. Is it clear, Sebastian, now? Can you please explain about stage 2 and how we consider stage 3 in it again? Okay. So when you are here, if I go back, this is what we have. This is stage 2. Okay. At stage 2, we want to remember that what we do at each stage is we decide here by considering the next one. Right? Here, what we say is we have one remained. We assume that, for instance, one remained for stage 2 and investment B and C, because you already put PA is equal to 3. If you have one here, this means that you already invested 3 in investment A. So 1 remains for B. And you have to keep an eye on C as well. Now, if you decide to go with 1 here, if you put all the money that you have here, 1, you will leave 0 money for investment C. If you have 0 for investment C, there is no money that you can get in return. And we said that you have 1 here remained, still PA is equal to 3. Now, if you decide to not invest on investment B, you will leave 1 for investment C, which gives you 4.5 for investment C and 0 from investment B. The total is 4,000. This is the way that we are going to consider the next one. So from stage 1, you know the decision. You have some money that you will consider for stage 2 and 3. Considering 3 means that your decision at stage 2 will impact the state in stage 3, the amount of money which remains for stage 3, and essentially your decision on that stage. That's how we consider the next stage. If you have more constraints, like investment in option C cannot be higher than, yes, that's fantastic. So you have to, when you're making a decision, you have to consider that. And we will see an example in the workshop. If you have some constraints like this, how you're going to treat them. If you have those constraints, then you have to, when you're making a decision, you have to make sure that you satisfy them and you respect them. Please explain how we came up with two optimal solutions in the example. With 0 and 1, both of them will give you 17. That's why we have two optimal solutions. If you just check them in the last table that we have here, essentially. So you can see that this one also gives you 17. This is also giving you 17. So there are two optimal solutions that we have. This was very unlike these ones in the previous stages. For each of them, here you can see again, this is like if you had one, the optimal action here could be 0 and 1. So both of them give you the same maximum return. As I said, you can Google them. There are like 4 or 5 problems that it will solve for you, and they're more than enough for this module. I don't expect you to become fluent in dynamic programming. So the ones that I will solve in the workshop, even not the ones that are like extra practices that are left to you, they're more than enough for as a part of this module. You will focus more in pricing analytics next time if you take them. If you don't, it is enough for the course that you have MSBA. So don't worry about that. You don't need you to be able to solve complex dynamic programming problems because they can be really complex. So don't worry about that. But if you want to solve extra problems, there are ones that I won't solve, and you'll have the solutions to them so you can practice with those ones. Catherine, but would for the second solution the other stage outcomes are lower? I'm not sure if I understand your question. Is the follow-up of another question that you asked? No. Can you elaborate? For explanation of two optimal solutions, the outcomes for stage 2 and 3 are different. Yes, of course they're different, and they should be. The only for multiple optimal solution, here we have two actions. Both of them will give us 17 in total. If you go with 0, as you can see here, if you go with 1, we'll have 3 remained for the next ones. And if you have 3 for option B, it's the best to invest 1 and leave 2 for the next one. And it gives you, and you will do 2,000 investment if you have 2 remain for the next, for the last investment. If you go with 0 here, you will have another action because you have state which is different from the previous one when you had 1 here. So if you go with 0, you will have 4 here. You have to invest 1, which leaves 3 to the next one. So there are different combinations that give you the same maximum return. Is it clear now? Okay, fantastic. No worries. Any other questions? All right, the number is also so low. Okay, can x1 equal to 3 in a stage? Can x1 equal to 3? No, it can't. For x1 to become equal to 3, this means that x1 is a parameter. Okay, don't forget that. x1 is a parameter, and it's the amount of money which remains for this stage. At stage 1, there is no decision that we made beforehand. So x1 is equal to 4. PA is the decision that we make for stage 1. This can be 0, 1, 2, 3, 4. So x1 cannot be equal to 3 in stage 1 because that's a parameter and that's the remaining money that we have for this stage. And it can be 3 because there is no decision that we make before this stage. Okay, fantastic. Okay, I presume you don't have any other questions. If you had, you can ask me next week, or you can ask during the workshop. Let me just stop recording. Until the workshop, take care, and we'll see you soon.